Alright, welcome back. Last time we had talked about finding the volume under a surface given by z is equal to f of xy that's above a rectangle. And the way we did that was we fixed the value of we fixed the value of x, and we found the area of one of the slices. And then we added all of those mini tiny little pieces of volume up together, and that gave us what the volume was under the surface. So you may be asking, why did we fix x and not fix y? What happens if we change the order of that? Well, here's a theorem that's just fun to say. Fubini's theorem says that if you have a continuous function and your region is a rectangle where the rectangle goes from a to b in the x direction, right? This is always the x direction, and the on the y-axis it goes from c to d, then you can freely interchange the order of integration. That is, if you took the integral here with respect to y first, and then with respect to x, that's the same as if you took the integral with respect to x, and then with respect to y. So, what does that correspond to? That's saying you could have sliced it in the other direction. We could have had a fixed value of y, figured out what the area is with respect to that y, gotten a little tiny bit of dy attached to it, and that's a little volume. So this is true if the function is continuous, or if the function is bounded, or if it's discontinuous only on a finite number of smooth curves, or if you know that the integrals exist. So when you have a continuous function, you're good. If you have maybe a piecewise defined function, also good. And if you have a function that doesn't get too high and it doesn't get too low, also good. So here's the takeaway message. When you have a nice function, you can choose the order of integration that makes your life easier. Let's look at an example. So let's say we have this function. We have a double integral over a rectangle of y times sine of xy, and this is our rectangle 1, 2 times by 0 pi. Which integration is easier to do? Is it easier to first integrate with respect to y, or is it first easier to integrate with respect to x? So in this function, if you look at it, what would it be if we had to integrate with respect to y first? Well, we have a product. So if we're trying to integrate with respect to y, this product, we may want to use integration by parts. You probably have to go and explore and figure out the right way to do that. But if we integrate with respect to x first, then our life is easier. All right, so here it makes sense to integrate first with respect to x. So we'll set this up. The integral from y is equal to 0 to y is equal to pi of the integral from x is equal to 1 to x is equal to 2 of y sine of xy dx dy. So remember, we're putting the x first because that's the innermost integral to do. And then we're putting dy second because that's the outermost integral to do. And so now we need to integrate sine of xy. So let's do substitution. So let u be equal to xy. Then du is equal to the derivative with respect to x, y dx. And so what do we get here? We get that, so y dx, so that's du. So we want to integrate from x is equal to, so if u is equal to x, So let's just keep the bounds. X equals 1 to x equals 2 of sine of u du. So the integral of the sine is negative cosine of u, evaluated from x equals 1 to x equals 2. So let's actually put back in what u was equal to. So this is negative cosine of x, y, evaluated from x equals 1 to x equals 2. So what do we get? We get negative cosine of 2y minus negative cosine of 1y. So in other words, after we've evaluated this integral, we've got something interesting happening here. We end up with this expression. So now it only includes y, which is normal. If there's any x's around, then you've done something wrong. And so this integral becomes the integral from y equals 0 to y equals pi of cosine of y minus cosine of 2y dy. And that's an integral that we can do. So an integral of cosine of y is equal to sine of y. The integral of cosine of 2y is cosine of sine of 2y divided by 2. And evaluate that from 0 to pi. If you look at this, what are we going to get? We're going to get a sine of pi minus sine of 2 pi over 2 minus sine of 0 minus sine of 0 over 2. All of these terms are 0, so we get an answer of 0. What is that saying? That's not saying that this function was the 0 function. It's saying that the total volume that was above the x-axis cancels out with all the volume that was below the x-axis. All right, so let's finish off by talking about some properties of double integrals. If you have a function that's a product of a function of x and a function of y, where the domain here is a rectangle, AB by CD, it's actually possible to take this integral into two pieces and do them each individually. That's saying, let's say we had a function like the double integral over our region of x, y squared over x squared plus 1 dA. And r is equal to the rectangle 0, 1 by negative 3, 3. What this property is saying is that if you look at this expression, we can write this as x over x squared plus 1 times y squared. So we're on a rectangle. Our function is a function of x times a function of y. So that means that we can write our integral only in terms of a function in terms of x times a function, an integral, in terms of y. And that can make our life easier when we're doing the integral. It makes things a little bit less clunky, a little bit less crazy to worry about. All right. Now let's talk about some regions that aren't necessarily rectangles. If you have the double integral of a sum, it's the sum of the double integrals. Yay, we like when that happens. If you have a constant, you can bring out your constant. And if you have one function that's always bigger than or equal to another function over your whole region, so you always have this one function, and it's always, well, the one function f is always bigger than or equal to the other function g on that region, then the double integral of the bigger one is bigger than or equal to the double integral of the second one. All right, let's stop there. See you next time.